Welcome to the course Introduction to Uncertainty Analysis and Experimentation. In this lecture, we will look at examples of uncertainty in a measurement. We will take the example of making a temperature measurement using an RTD sensor or a thermocouple sensor along with an indicator. Temperature measurement is probably the most extensively conducted measurement, not just in industry or in experiments, but also elsewhere, as we are seeing in COVID checking. It is one of the most trickiest measurements. There are many techniques for making temperature measurement. Their accuracies, the cost, everything comes in a wide range. We will take one simple example of a sensor, which will be a thermocouple sensor, and see, we will connect it with an indicator and look at the situation where we have not done the experiment, but we want to assess that if we get this particular thermocouple RT and indication combination, what uncertainty can I expect? So, this is an example of pre-test uncertainty analysis in a measurement. So, here it is the problem statement. We want to select a temperature sensor and an indicator with or without controller for engine coolant temperature measurement about 90 to 110 degrees Celsius. How can I compare different makes and models and what uncertainty to expect? So, this is one application I have listed. In the example, I have taken yet one more example, which is a temperature of a flue gas. And the temperature we have said this is approximately of the order of 150 degrees Celsius. So, this is the application. It could be in general anything where the fluid temperature is about 150 degrees Celsius, in that range. And this range matters because, as we shall see, the uncertainty will change depending on the temperature being measured, even if it is the same instrument. So, let us see first step in our procedure: study instrument, sensor and its associated electronics and data acquisition system and their specifications and data sheets, and including web based information. So, if you go to the web and start asking what are the type of sensor available, what are the type of indicators that I can have, what is any other permutation combination that is there, you will get a very large number of options, and then you have to decide how to go forward. The first thing is, let us get the information, and here I have displayed some samples of what you would expect to see. All these are from particular manufacturers. There is no real preference. I am using these for illustration only. So, this is a type of a sensor. You can see here these pictures, and what they have is, and outside there is a stainless steel tube, a hollow stainless steel tube. So, you can say it is like this, closed at one end. Inside this, here we have our sensor, and here there is a packaging which is closed, and finally, there will be wires which can be connected, and this side you have arrangements to fix it to something else. So, this is the fixing arrangement here, and from this your wires can be taken out. So, there will be a connector inside. which has got screws on which you can connect it, and the sensor is sitting inside this stainless steel tube. So, this is a typical arrangement which is called a shielded sensor. And what it does is that the element does not come in contact with the environment in which the measurement is being made. Sometimes these environments can be quite harsh and they can damage this device, and so thermocouples, in some cases they can be just without the shield and in the domain, but RTDs are always with a shield, and so are the NTC, which is written here, negative temperature coefficient or thermistor. Now, from this data sheet, let us see what we can learn. It says that accuracy, okay, this side is thermistor, this side is the RTD, the resistance temperature detector. So, the thermistor works on the principle that you have a device whose the temperature increases, its resistance decreases. So, that is the negative temperature coefficient. RTD is a resistance temperature detector, which has a small platinum element, a small wire element or a foil, and as the temperature increases, its resistance increases. So, what we are measuring in both cases is a change in resistance, and from that we are interpreting what is the change in temperature. So, for the RTD it says that the accuracy is better than plus minus 3 degrees Celsius from minus 40 to plus 300 degrees Celsius. So, over this range, accuracy of this is plus minus 3 degrees Celsius. For the thermistor, it is a little more involved thing what you can see here. It says minus 40 to plus 25, the accuracy is plus minus 2.5 degrees Celsius, minus 25 to 100 plus minus 0.8 degrees Celsius, 100 to 125 plus minus 2 degrees Celsius, and 120 to 150 degrees C plus minus 3.5 degrees Celsius. So, this is an example where the accuracy is a function of the range of the measurand. And this happens in many other instruments also. So, we have to do a two-way adjustment in the experiment design, that if you want maximum accuracy, you may have to make a compromise and go for low temperatures, whereas if you want to work at this temperature, then this option is precluded, we cannot use it. So, that is the accuracy about these two devices. Now, let us look at thermocouples. So, the principle of a thermocouple is that we take two different types of wires and fuse them at one end to make what is called a bead. It looks like a small bead, and we fuse this also. And then we make the electrical connection, that we connect these two either directly or through a common wire, and then we connect these two to an indicator which tells us the voltage. Then we subject this and this to different temperatures. One, so this is say a higher temperature T h, this is the lower temperature T L, then the EMF produced is proportional to the difference T h minus T L. So, if we can measure this by measuring a change in the EMF, so we measure change in EMF, from there we get delta T, which is the difference of these two temperatures. And now, if you want to know the temperature of this or this, we need to know the temperature of the other junction. So, one junction we call it the reference junction. And one very good reference that we have is the triple point of water, 0.1 degrees Celsius. So, if we keep one as the reference junction as this one, then we add this value to this delta T and we get TH. So, that is how the thermocouple works, but the signals are very low, and so what we do is send it to an amplifier and then digitize it and then do this reverse calculation, convert the EMF into a delta T, we need a calibration there, and then add the reference junction temperature to it and we get the temperature that we are trying to measure. So, when we are measuring, it is this part here which we will take and locate it where we want to make the measurement. Now, thermocouples come in a few common categories or types that they are called, and that is listed here. So, this table is taken from an international standard which governs thermocouples. So, this is the international standard IEC 60584, and there are equivalent standards from ANSI, ISO, IS. So, when you look up a manufacturer's catalog, they will all say that this thermocouple is as per IEC 60584, and within that they will give more information that what is the type T, J, E, K, all that tells you what is the type of the material of the two wires. We said there are two wires here, this wire, and this tells you what is the material of those two wires. And then it tells you about the accuracy. So, that there is tolerance class 1, tolerance class 2 and tolerance class 3. And we will look at, say, the type T thermocouple, where there one wire is of copper, the other is of constantan. And it says that if you have class 1 thermocouple with this, you can expect a temperature, we can expect an uncertainty of plus minus 0.5 degrees Celsius or the value times 0.004, whichever is greater. For tolerance class 2, for the same range, we have type T, which is good for minus 40 to plus 350 degrees Celsius, plus minus 1 degree Celsius or plus minus the temperature multiplied by 0.0075, whichever is greater, either this or this. And for class 3, it is plus minus 1 or the temperature measured into 0.015, whichever is greater. So, this is the highest accuracy, then less accuracy and the least accuracy. And there are similar numbers given for each type of thermocouple and the range over which it can be used. So, for instance, here type K type thermocouple, which is nickel chrome and nickel aluminum, or called chromel alumel. This works from minus 40 to 100 degrees Celsius, plus minus 1.5 degrees Celsius, or if it is class 2, it goes to 1200 degrees Celsius, plus minus 2.5 degrees Celsius, the uncertainty is there. So, this is a table where we have now learned that even without buying anything or having an instrument with us, if we can look up IEC 60584 or any of its equivalent standards, we know what accuracy to expect in these type of devices, whose picture is shown on this side here. So, what you are seeing here is, in this case, this is the shielding, stainless steel shielding. Inside this is the thermocouple, the wire is coming out there and it is connected at the other end to a plug, which is the connector. This is a picture of something where there is no shielding. This is the bead you can see here. This is called bare bead. and then it has got its wire which is made into a coil, and finally it has got a connector over there. And this is a configuration where you have a shield, inside that is the thermocouple, and right on top itself is the connector integral to this body. So, there are very large number of permutations, combinations that are available standard, and on top of that you can yourself design your own sensor also. So, that is what we have seen about thermocouples, and this is the same chart put in a different way, but the values here, this is also from IEC 60584-2. So, there are different websites that one can look up, and there are many more. So, this is just a representative sample here. Now, let us look at the other part of the device, that we take that connector, we saw that it is ended up in a wire. That wire can be connected to an indicator, and so this is one example of an indicator here. The website from which this is taken is over here, and I am using this for illustration only. So, it gives the technical specifications here. It says input type can be JKTRS thermocouple or RTD PT100 thermocouple or a current input or a voltage input. And the display range is as per this table, it says. So, we are going to look at T type thermocouple. The display range here is -200 to 400 degrees Celsius. Then accuracy, it says for thermocouple plus minus 0.25% of full span. Full span means in this case we are going -200 to 400, which is 600 degrees Celsius. So, 0.25% of 600 degrees Celsius is this thing plus 1 degree Celsius. So, if you want to calculate this, this becomes 600 degrees Celsius into 0.25% plus 1 degree Celsius, and this you can see this is 2.5 degrees Celsius. And it does not matter whether you are measuring -100 degrees Celsius or near 0 degrees Celsius or 350 degrees Celsius, the uncertainty or the accuracy of this is the same. That is one piece of information we got about what to expect on the indicator. The next thing is that, as we have learnt in measurement, thermocouple output is an analog signal. It is amplified, finally digitized, and then displayed or recorded. So, in this case it says A to ADC resolution 16 bits. That means the entire input signal that was coming in, it has been programmed in a way so that the full scale of temperature, which translates into a full scale of voltage which the instrument sees, that is divided into 2 to the power 16 bits. And we can then see that if this was our input range, this 600 divided by 2 to the power 16, this will tell us what is the minimum temperature difference that this particular indicator can discriminate in the digital form. So, that is one more piece of information we have. We have got this one, we got the other one there. So, this was one, this is the second one, and now let us look at the third one. It says display resolution 0.1 degree C / 1 degree Celsius. So, depending on where we are measuring the temperature, what we see here is got 4 digits on the display, they have shown here. So, as you can see in this picture, the decimal is over here, in which case we are looking at display resolution of 0.1 degree Celsius, whereas here we are looking at a display resolution of 1 degree Celsius. So, this is, we can select this. So, this is a third piece of information we have about this device, which influences the uncertainty that we can expect in using this device along with a thermocouple or an RTD or just a current or a voltage measurement. and it also says what type of inputs it can take. So, these are the thermocouple inputs it can take. It can take an input from a PT 100, which is a resistance temperature detector, good from minus 199.9 degrees Celsius to 850.0 degrees Celsius. And it can also take inputs as voltage 0 or 1.5 volts, 0 to 1 or 0 to 5 volts. So, you can input a voltage to it, or as we can see here, this says 0 to 20 milliamperes or 4 to 20 milliamperes over a range minus 1999 to 9999. So, as I was mentioning, many instruments in the real world which are used in process control and all that, they would all have on the top of the instrument a transmitter which will convert the signal into an equivalent current signal and send it out. So, this signal could be 0 to 20 milliamperes or 4 to 20 milliamperes, and then it gets into that much, that is the range of over which this signal will come. So, minus 1999 will correspond to, say, in this case 0, and 9999 will correspond to 20 milliamperes. So, if the temperature indicator was transmitting a current signal, we would use this. What we will do is we will say we will directly connect our temperature sensor to this indicator and see what happens. So, we are not wanting to get into this part for now. But in the real world, this is how things will happen. One will have to work with one of these things because the distances would be long. You do not want signal attunement, and so that is what you do. Then there are many other specifications given here, like sampling rate, 5 samples per second. So, in every 12 seconds, it can take a reading. Then cold junction compensation error plus minus 3 degrees Celsius. So, this is another thing we could look at, that if our cold junction is not an ice point will not give this problem. But if we do not have an ice point and we rely on the cold junction in the device, then we are looking at yet one more source of error. Then these are all electrical aspects, we do not need those here. The last part here is, of course, it has got a 4-digit display, and we can see from this indicator what it looks like. So, this is the indicator we will try to connect to a thermocouple. So, that is, and if you look up the web, you will find many more indicators and you get lot more information about their technical specification. So, this is a typical one that we are looking at. So, here is yet another one, but this time it is for RTD, which is the resistance temperature detector. This is also very widely used in industry for temperature measurement, although it has to be used with a stainless steel shield, whereas the thermocouples we can use it without a shield also, and those could be much smaller also than RTDs. So, they have their own pros and cons, and depending on the application we have to make a call. So, it says RTD elements, the terminology is given there, and accuracy, it says the statement of the initial element accuracy as measured at one point only, usually 0 degrees Celsius. So, here is the information given here. For typical resistance of RTDs is 100 ohms. These are all platinum elements. Platinum is a noble metal, so it does not corrode or degrade in that sense. Accuracy is plus minus 0.1 ohm at 0 degrees Celsius. So, this is plus minus 0.1 ohm, and repeatability is plus minus 0.1 degrees Celsius over the temperature range. This is pretty good repeatability. That means, if you come back to the same thing with the same instrument again and again, you will get all temperatures which are within this much. And then here is the tolerance information at different temperatures as of, so as a function of temperature, how does it change? this is the table that is there. So, in degrees Celsius at its minus is 1.2 degrees Celsius at minus 20, it decreases to 0.3 at 0 degrees Celsius and again increases to 4.4 degrees Celsius at 700 degrees Celsius. So, RTD also has got a similar situation that we saw for a thermistor, that it has the best accuracy point in some range. At the far ends of the instrument, its accuracy decreases. So, that is another indicator which we could use along with this or with the thermocouple, and it says you got 3.5 digit or a 4.5 digit display. The half digit is that this is 1999. So, this digit does not go beyond 1, it is maximum is 1 and the maximum number it can display is 1999. It can take JK thermocouples PT 100 or 4 to 20 milliampere input current. And then again it gives it is not good. So, if you want to use T type thermocouple, this is not suitable, we cannot use it. But let us see what else it tells us. Accuracy is 1%, RTD it is 0.2% and for current it is 0.1%. And there are the various models that are there. So, here is a slightly different type of a device, but it is not good enough for T type thermocouple. Now, let us look at some standards. For resistance temperature detectors, which is called platinum resistance thermometer sensors, this is what we have been calling RTD. We have IS 2848, which is the latest version, which is few years back, and it gives us what all is there in this for getting the details of the sensor. So, this is one standard and we can freely download it and have a look at it. But as far as RTDs goes, there is an international standard, you can see here, IEC 60751. IEC, as we have seen in ISO GUM also, they were part of the process, International Electrotechnical Commission, and this is a standard on industrial platinum resistance thermometers and platinum temperature sensors. So, much of what is there in IEC 60751 has been incorporated into IS 2848. So, we are, if you do not find this standard, we can definitely get the Indian standard. So, this is one standard for RTDs. Similarly, for thermocouples, here there is a standard IEC 60584 part 1, part 2, and as we saw instruments, sensor manufacturers, they will say our sensor is class 1 as per IEC 60584, and what it mentions, we saw that in one of the earlier slides. So, the title of this here is thermocouples part 1, EMF specifications and tolerances. So, there is also an equivalent Indian standard on this one. So, we can look up that, but we saw how if someone tells us that this instrument is in conformity with IEC 60584 class 2, then we know from that earlier table what they mean. We do not need to separately ask them what is the accuracy of this instrument. So, that is some more information we got about standards, and as you look up catalogs, you will find all the good manufacturers will say that their sensors conform to one of these two standards or an equivalent standard. There are some instruments where everything is together only. So, here is one example of that, portable temperature indicators from this one particular company. So, that means there is a sensor and it tells you the temperature and humidity in one shot. So, it gives here sensor is K type thermocouple, chromel, alumel. It can go in temperature ranges minus 50 to 750 and even up to 1200 degrees Celsius. Resolution point plus minus 1 degree Celsius. So, this is one input that you would read if you are looking at uncertainty from this. Then accuracy, it shows you that for different temperature ranges the accuracy is different. So, we have to be picking up that value of this accuracy where we expect to make our temperature measurement. If our expected temperature measurement is 100 degrees Celsius, we would pick up this one, 0.75% plus 1 degree Celsius. If you are making a temperature measurement of 800 degrees Celsius, it would be here, 2% plus 1 degree Celsius. So, it says 0.75 plus slash 1 degree Celsius, whichever is greater. So, that is the accuracy, that is another piece of information we would like to have. Then there is cold junction temperature display, 3.5 digits, sampling time 0.4 seconds, and then the rest of the information is there. So, this would be a case like we saw with the infrared temperature measurement device, where we do not know what is inside the electronics in this, we just know these broad parameters and we have to work with the indication that the instrument gives us. So, now we will get into our example. We say what we will have is a system domain where in steady state we are having a temperature of about 150 degrees Celsius. In that, all these devices, thermocouples, RTDs and thermistors, they are intrusive devices. So, in the catalogs and everywhere you will see that it says immersion. So, what is the environment in which they can be immersed, what is the pressure, temperature, what are the chemical composition of that environment, all of that will come over here. We will use a sensor thermocouple T type and take its wires and connect it to an indicator or logger that we saw in one of these pictures here. And we will say that, look, I want to make such a measurement in my experiment in the future. When I make my experiment, if I use this particular sensor and I use this particular indicator or data logger or a DAS, then what is the overall uncertainty I can expect in my temperature measurement? This is the question, which we know that for this we need the multiplying factor and the standard uncertainty in the value, and for this we need to get S T bar and B T bar, and then in each one of these we have some things coming in. So, we have to calculate this, we have to estimate this, then calculate this, estimate this, calculate this, then come here, we got the answer. So, that is what we will do now. So, first the same step by step procedure that we have seen earlier, we say compile all data from measurements. Now, we are in the pre-test stage. We do not have any data, either we can set it to 0 or we can use some number from our experience. So, this step goes away. Here it is using the data calculate the mean value of the measurand, where we do not have any data, this step also goes away. This identify all possible elemental sources of error and not influencing one another. So, we are again and again saying these are uncorrelated errors. And what we see here, we can say that, look, from the instrument, the sensor thing, I got the accuracy of the thermocouple. Then the indicator gave us some data that it has got its own accuracy. So, that is another source of error. Then the same indicator has a display resolution, that is another source of error, and A to D conversion, that is another source of error. So, we have j equal to 0, k equal to 4. So, j was the number of independent sources of random uncertainty, elemental random uncertainty, and this is the number of sources of elemental systematic uncertainty. Now, we see what all data we have. We could have had more things, but we may not have data, which is what this thing tells us. But we have got all the things that we want, and we can estimate our uncertainty from this. So, the next thing is about calculating the random standard uncertainty, and we said, well, we have no data. So, we have an option, either we set it from experience, some number, but for now we will just say it is 0. Now, how do we estimate the standard error from each one of those answered error sources? So, that is our 7th step was estimate Bxik for each elemental source. This k is a small k. We have k equal to 1, 2, 3 and 4. We had 4 elemental sources of systematic error, and now we go one by one, see what happens. So, number 1, accuracy of the thermocouple. We are measuring 150 degrees Celsius. We have a T type thermocouple, and let us say we got class 1 thermocouple as per that IEC 60784, which said that the accuracy is plus minus 0.5 degrees Celsius or 0.4 degrees Celsius of reading, whichever is greater. So, 0.4% of 150 degrees C becomes 0.6 degrees Celsius. This is greater than 1.5 degrees Celsius. So, we use this value, and assuming that this is a reported number at 95% confidence level, that is 2 sigma. So, the standard elemental standard error due to accuracy of the thermocouple is 0.6 divided by 2, which is 0.3 degrees Celsius. That is systematic uncertainty source number 1. Now, I look at number 2. This is accuracy of the indicator. The first one was accuracy of the thermocouple. And from one of those earlier catalogs, we decided let us take this particular indicator and see what it has got. It says plus minus 0.25% of full span plus 1 degree Celsius. And we saw that the full span was minus 20 to 400 degrees Celsius, which is 600 degrees Celsius. So, this becomes 0.25% of 600 degrees Celsius plus 1 degree Celsius, which is 2.5 degrees Celsius. And again we go with 95% confidence level, 2 sigma. So, our standard error due to accuracy of the indicator BT2 bar is this value 2.5 by 2, which is 1.25 degrees Celsius. Our third source of uncertainty, systematic uncertainty, was display resolution, which was 0.1 degrees Celsius or 1 degree Celsius. Let us say we will configure it for 0.1 degrees Celsius, and in this case we say that the uncertainty will always be plus minus 1 digit. So, BT3 is 0.1 degrees Celsius, which is a standard error due to display resolution. And for A to D conversion, we saw that it was 2 to the power 16, it was 16-bit converter. That means the input got divided into 2 to the power 16 parts, and that was used to convert the full span into equally spaced bits, and that becomes 9.155 into 10 to the power minus 3 degrees Celsius. So, at 95 degrees confidence level, this becomes this by 2, which is 4.6 into 10 to the power minus 3 degrees Celsius, or this is 0.0046 degrees Celsius, or we could even have been quite okay with writing 0.005 degrees Celsius. So, there we are. We got the 4 values that we were looking for. one is over here, sorry, one over here, the second is here, the third is here, and the fourth is here. Now, we will put them all together as it says here in table number 2. So, let us see that. So, table M2, estimate Bxik, this is k is small, and enter in column 5. So, we have done that. Accuracy of the thermocouple Bt1 bar 0.3 degrees Celsius. Accuracy of indicator Bt2 bar 1.25 degrees Celsius. Display resolution Bt3 bar 0.1 degrees Celsius. A to D conversion Bt4 4.6 into 10 to the power minus 3. So, we got all the things in one go, and just by looking at it, now we start seeing some interesting things, that this value is 0.0046, much less than any of these three. So, A to D conversion, we could even say that I can neglect this. The other thing, by looking at it, we look at this number 1.25, others are 0.1, 0.3, almost like this is 10 times this and at least 4 times this one. So, this is a big uncertainty which will reflect in the final uncertainty very significantly. So, we could even say that this becomes the dominant elemental systematic uncertainty. So, it helps us in a way that if we want to make the uncertainty less in the measurement, well, do not worry about thermocouple, it looks good shape, we picked up the right thing. Remember, we picked up class 1. If we had picked up class 2, this number would have been bigger. And then we said indicator, we should get a better one. A to D conversion, this is more than good. We have 16-bit converter, that is really good. Had we used say an 8 or a 10-bit converter, this number would have been comparable to say this or this, and then uncertainty coming in due to A to D conversion, that would have been significant. In that case, our strategy would have been increase the number of bits in the A to D converter, and then we could say, okay, I will take this one with the 16-bit converter. Then the uncertainty due to conversion is negligible. But as you go from 8 to 10 to 12, 16, 20, 22, 24-bit converters, the cost increases substantially. So, we have to be ready for that. Now, we go to the next step. We put all of these things together and calculate the systematic standard uncertainty in the temperature. We sum of the squares of all these numbers, which is this much, which we can say is 1.3 degrees Celsius. And although it is coming as a squares, you can see now this one dominates much more than this one, because further we have taken squares. So, this is definitely something that should be of concern to us if we want to improve this. If 1.3 degrees Celsius systematic standard uncertainty is okay, good enough for what we want to do, then we do not need to do anything else. We could then think of, can I reduce the cost of my device? Instead of an indicator with 16-bit converter, can I go for a converter with say 12-bit converter, an indicator? It will reduce my cost, and this may not change too much. And all of this is possible because in the pre-test stage. Then we come to the complete summarization of everything that we have. This is the table M3, and here we can see that description, well, we want to make a temperature measurement in about 150 degrees Celsius environment. 150 could have been 120 to 180, 200, that is okay. Mean nominal value V bar not applicable. We do not have data, we are in the pre-test phase or the design phase. Random standard uncertainty we have assumed to be 0. We could have put a number here based on experience, say plus minus 0.5 or maybe plus minus 1, and then done the calculation and see what happens. Systematic standard uncertainty, we have done the calculation BV bar, this is equal to 1.3 degrees Celsius. We are now writing the units in this case. Combined standard uncertainty, UV bar is equal to SV bar plus BV bar, which is 1.3 degrees Celsius. Confidence level, we are going to go with 95% confidence level, which gives us KCL is equal to 2. So, that is 2 over here. Expanded uncertainty in temperature, this should all be T, sorry. This is UT bar, which becomes 1.3 into 2, 2.6 degrees Celsius. So, this is also T. And finally, relative uncertainty we cannot compute simply because we do not have the mean value over here. So, this was not there. So, this is not applicable. So, having done all that, this is the number that we wanted for which we did this whole exercise. So, all of those that steps in the table we have put here. UT bar is equal to 1.3 degrees Celsius. We define the confidence level KCL as 2. Then we calculate expanded uncertainty in the measurement UT bar, and this is KCL times UT bar 2.6 degrees Celsius. And then we calculate the relative expanded uncertainty in the measurement. We do not have this value, so not applicable. And finally, we express the result. In this case, as a percentage, we cannot do it. We just say that the uncertainty in the temperature measurement will be plus minus 2.6 degrees Celsius at the least. On top of that, we could have added random standard uncertainty. So, with this selection of sensor and indicator, this is what we could expect. We will take a small discussion on analog to digital converters. We have already seen that. Now, let us see what are the type of converters that are there, and this is from one of the manufacturers, and you will see lot more of these. So, what they have is like a small box in which on one side we connect our analog inputs, and the output could be typically now a USB cable. So, let us see what they tell us. If you have to select a to D converter, and from there we get the uncertainties due to the digitization, here is what we have to see. So, they say that this particular case 16 differential or 32 single ended analog inputs expandable to 32 differential / 64 single ended channels. That means, differential means when you have both signal wires coming in from each instrument. So, from one sensor we got 2 wires, we saw that in the thermocouple. So, this is thermocouple number 1. Then we got 2 more from thermocouple number 2. Like that, if we have this is the differential mode, we can put 16 things. Single ended means we put only 1, and all the other wires we make it common and take it as a single input, in which case we can get 32 signals in. It says that this particular A to D converter 24-bit resolution, it is pretty good. 2 to the power 24 is what it will divide the signal into, that many bits. This is very good, and you will see that with the type of errors and uncertainties that we get in practical life in making a temperature measurement, for instance, this thing won't matter. It might be an overkill, because the uncertainty due to this, as we saw, is negligible already. 2 to the power 16 was a very small uncertainty, 2 to the power 24 will be none, practically none. The input here can be thermocouple or voltage, and then it says what is the input range that we can select. And it says 9 software selectable input voltage ranges. So, in the driver software we can decide what is it that we want. So, range is varying from the top here is plus minus 20 volts, then there is 10, 5, then there is plus minus 2.5 volts, and then it goes down and comes down here to plus minus 0.312 volts, and the least it can take 0.078 volts, or this is nothing but plus minus 78 millivolts. So, it gives you a lot of flexibility here. Now, remember thermocouples have sensitivity of the order of like 40 microvolts per degree Celsius, maybe going up to 75 microvolts per degree Celsius, depending on the type of thermocouple. It is T or K or what, and there are some which are even less than this, maybe 20 microvolts per Celsius. So, if our temperature difference is 100 degrees Celsius, then we will get, say for in this case, 40 into 100, which is 4000 microvolts or 4 millivolts. Now, what we see is that no matter what we do here, even at the smallest range, we are going to be using only a very small fraction of this 78 millivolts. Just a few bits out of the 2 to the power 24 bits will be used, the rest will lie unused, and we will not get that fine difference in the measurement. So, the only option is that we amplify this into something. So, we need to have an amplifier. And this particular device does not have this amplifier. So, we have to get a separate amplifier, or we could get 0 to 20 milliampere signal and then work with that. So, we can amplify it and bring up this 4, say if you multiply it 20 times, then you will be 80 millivolts, but you will be going out of range for this. Maybe you can try this one, but if you go here with 80 millivolts, you are only using half the available scale. So, there is a compromise being made. So, like this we will have to go back and forth and say, okay, I will have x instead of having x 20, I will use x 50 times amplification. So, I get up to this into this is 200 millivolts, 0.2 volts, and now you can see that this might be the best one to use. So, that is the type of calculations you have to do to decide what is it that you really want. Then it gives 1000 sampling rate, and then there are counters, and then the remaining thing over here. So, that tells us how amplifiers and the input signal. So, this could be a thermocouple input, or if it is just a voltage signal in that range, it makes no difference, the instrument will, this device will take it. And that is the way in which you have bits as an issue, range as an issue, this was one, and amplification as an issue. And when you are designing an experiment, you got to match all these things together, so that you do not chop off the signal or go out of range, and we do not end up having to use a very small fraction of the full width of the A to D converter. For thermocouples, we have to worry about another thing. The reference junction is an issue, and this can be quite significant, as we saw in that one of the catalogs. If the best practice is to use ice point, because it is simply very easy to make. It is nothing but take a thermos flask, put ice, water, and make sure that it stays as ice and water, and you will be at 0.01 degrees Celsius. Hopefully that water is pure or very clean, RO water or distilled water. And to convert for the thermocouple, EMF into delta T, we have here, as you can see, ITS table, International Temperature Scale table, reference junction 0 degrees Celsius. So, one could say that, well, what voltage did I get? And you say I got 4.046 millivolts. So, this is in millivolts. Then you say, well, my temperature difference was 95 degrees Celsius. And we could even interpolate between that, maybe to 1 or 2 more 2 decimal places, depending on how good our other instruments are. So, that is what tells us that if I just measure EMF, I will use this table and get a temperature. But there is a problem. This thing is applicable for a thermocouple made according to those standards. And the standard includes specifications on the quality of wire, the quality of the bead which is made by fusing, many other things. So, if you have to go by wires which are of that quality and make a bead by that process, you will have to spend a lot of money, and if you buy something which is made that way, it will be more expensive than what you make yourself. So, if you make the bead yourself by wire which is not exactly the top grade wire in this, but medium or a lower grade wire, which is what we normally will end up using, then we make a thermocouple and measure the EMF and use this table, then we will be off. So, that introduces a systematic error called the calibration error. And this will result in its own elemental systematic standard uncertainty. The other thing that we could do is we take our thermocouple and with whatever we have, we make a curve fit. So, we take our thermocouple, we make 2 reference junction, 2 temperatures. One is of course ice point, and then we use say the boiling point of water and boiling point of alcohol or some other material. There are about a dozen and a half standard temperatures which have been defined, which we can create in the lab and measure at these points and see what is the delta EMF we get, and then we know that that corresponds to certain delta T. So, at least 2-3 points, if not more, we do this thing, and from here we get a curve which tells us that delta T is equal to this function of delta EMF. That is a curve fit, that is not calibration. So, this will introduce yet another systematic error in the measurement. In the example I gave, we did not have to worry about it because the indicator itself had all these things built into it, and after doing all that, they have quoted the error or their accuracy of the device as something. So, they took care of these things, especially calibration. So, those were some examples of how to go about doing uncertainty in a measurement. Many of the terms that we had looked at in the lectures now came alive when we looked at practical examples. All of this gives us in the end the uncertainty in the measurement, whether it is the pre-test stage or the post-test stage. This value we take over to doing estimation of uncertainty in the result. So, on that note we conclude uncertainty in a measurement. Thank you. With this discussion, we end our lectures on uncertainty in a measurement. Next step is uncertainty in the result. Thank you.